Paper 1 2017, a tricky question this, and a bit of a longer question on transition metals. So we've got our table to refer to, but a couple of new things in here. State the type of bonding between oxygen and hydrogen in this compound. Well, the bonding between oxygen and hydrogen is actually within the water molecules. They're covalent. It's a coordinate bond or a dated bond between the water molecule and the copper. Actually, in the water molecule, between the O and the H, it's actually a covalent bond. Why the chloride ions in this compound are not considered to be ligands? Because they're outside of the complex. The ligands coordinately bond with the copper, but that will form a 2+ ion, and the Cl2 minuses will be attracted to that. But the Cl2s are not ligands. It's got 6 water molecules around it, 6 water ligands around it, which are forming coordinate bonds, but the Cl minuses are not. They will just be dissolved probably in the solution. They don't form coordinate or dative bonds. They don't donate lone pairs of electrons. They're not ligands because they're not forming coordinate bonds. An excess of ammonia is added to the sample to form solution B. Well, a bit of a tricky question this, because what happens is when ammonia is added, first of all it forms the hydroxide CuH2OOH2, because ammonia here. Ammonia forms ammonium hydroxide, as we talked about before, and the hydroxide part replaces 2 of the waters and makes ammonium ions. But then it goes on to react again, and 2 of the waters and the 2 OH minuses are replaced by NH3s. So you form 2 waters and 4 NH3s, and it's 2+ because the waters and the NH3s have no charge and the copper's got a 2+ charge, and it forms this deep blue solution. So you can cut out the middle part if you want to, and just say that the copper H2O, when we had excess ammonia, forms CuH2O2 NH3 4 2+. And so you could write the equation like that: CuH2O 6 2+ and 4 NH3s. 4 NH3s replace 4 of the waters and leave 2 of the waters remaining, and it's 2+ charge because the ammonia and the waters don't have any charge, and the Cu is still charged 2+, and 4 of the waters come off. So you could jump from the CuH2O6 2+ straight through to that CuH2O2 NH3 4 2+. It's a deep blue solution. It's there as a deep blue solution. Okay. Sodium carbonate, what does it make with copper? Just got to learn it. It makes copper carbonate as a bluey-green precipitate. Reagent D was added to another sample of solution A to form a yellow-green solution. Identify D. This is tricky. Cl minuses are big, and so you only get 4 Cl minuses instead of 6 waters, because waters are small and Cl minuses are big. Now, it's a tricky question this, because it's not well known that when you replace waters with Cls, Cl complexes like this, CuCl4 or FeCl4, are greeny coloured. So the clue is that it's yellow-green, and you've used hydrochloric acid. After all, that's a strong acid, and we're dissociating water to make Cl minuses to replace the waters. But you only get 4 Cls around it because they're bigger than the waters, and only 4 Cl ligands can fit. How come it's 2-? Because the copper is 2+, H2O's got no charge, Cu 2+, 2+ overall with no charge on the waters. If that's 2+, then the Cls is 4 Cl minuses, 2+ and 4 Cl minus leaves 2- left over, and it balances with the 4 Cl minuses there. Explain colorimetry cannot be used to determine the concentrations of solutions containing CuCl2 because it must be because that's copper 1, CuCl2 1-. That must be copper in 1+ oxidation state, Cl minuses of -1 each. There's 2 minuses there, 1 minus left over. 1 plus -1 minus 1 leaves -1. That copper's in 1 plus oxidation state, and it must have a full 3D shell. So it must have a full 3D shell. It's not got a partially full 3D shell, so it cannot absorb visible light. It's copper in a 1 plus oxidation state. Tricky question that. But you know that transition metals, if they've got incomplete 3D orbitals, absorb visible light and are coloured. If they've not got incomplete 3D orbitals, they can't promote those 3D electrons between the 3D energy levels and absorb visible light. Ethane dioate here, that's the formula of ethane dioate. It's got 2 carboxylic acid groups on the end that have released H pluses. You could write it as C2O42 minus. Again, unfortunately, you've just got to learn that C2O42 minus ethane dioate. Ethane dioate is, you can see there's lone pairs on the O minuses. That's going to form a bidentate ligand. So these 6 water molecules can still have, can be replaced by 3 ethane dioate ions, each forming 2 coordinate bonds each, and that's why you only need 3 of them. The coordination number will still stay as 6 because there's still 6 coordinate bonds, but you only need 3 bidentate ligands. Ethane dioate and 1,2 diaminoethane are bidentate ligands. Why the enthalpy change stays the same, or roughly stays the same number of bonds being made and broken, because they've still got 6 coordinate bonds around the Fe. Still got coordination number 6. Draw the displayed form of the ion complex produced in the reaction. So again, you just put 3 of these round, and you should really draw the lone pairs of electrons on the O's and do arrows towards the Fe to show that there are coordinate bonds with the electrons donated from the O's to the Fe. 6 bonds around it, so it's going to be octagonal. 4 in the plane, 1 up, 1 down. 6 bonding pairs, 90 degrees. When you get bidentate ligands, or a multidentate ligand like EDTA around it, and you get optical isomerism, you get a strange situation where you can have mirror images and enantiomers of each other. Ethane dioate is poisonous, but it doesn't seem to poison people who eat these foods. Maybe the ethane dioic acid, ethane dioate is only present in small amounts. That's why it's not killing people.